So I probably won't be able to do all of this, but I'll just like give it a time. Okay, so first I want to look at the oil ground. So when you have a minimization problem like this, there's this associated PDE that we call the Euler-Lagrange equation. So we have that if omega is a minimizer, then, okay, I won't be too rigorous, but basically the boundary of omega satisfies this PDE. So the curvature plus 2 times something, I'll define that, minus some constant equals 0. So if we were just looking at the normal problem where the energy is this parameter, this wouldn't be here, right? So it would just say that the curvature is constant, and it will be a ball. So we have this new term here, and this term it's like potential energy. So V of x is defined to be integral over omega of dy over minus y to alpha. So it's like, you're taking x inside your domain and you're taking the potential energy around it. Okay, so the reason I introduced this is we can use this to find when the minimizer is convex. And I won't show you how, but you can see, right, since this involves the curvature, right? If we can somehow use this to bound the curvature from below, and say that in certain parameter regimes, the curvature is positive, then we can show that the minimizer is convex. So, and the reason we want convexity is because we have this Bonson inequality. Is anyone familiar with this? Okay, so basically the Bonson inequality is, suppose you have a set, right? You can define the isoperimetric deficit of the set, which is just, you take the perimeter, you divide it by the perimeter of a ball of the same area, and you subtract 1. So it's a measure of how much more perimeter you have than that of a ball. So what this Bonson inequality does is it relates the isoperimetric deficit to how much the boundary deviates from a ball. Okay, so if you have omega convex, then you have that it lies in some annulus where the width of the annulus is 2 delta. And delta is small in this sense. So delta is going to be less than or equal to the area times 2 plus the isoperimetric deficit. What is that? So do you intuitively, so this is basically saying that if your perimeter is close to that of a ball, then the boundary doesn't wander too much from this annulus. And this is for convex sets. Okay. So remember, our goal now is to find for what parameters we know the minimizer has to be a ball. So the basic idea is, it turns out that if you know the mass is small, then you also know that the isoperimetric deficit is small, and that will tell you that it's close to being a ball, and then somehow you can use that to bound again, and you iterate, and you actually get that it has to be a ball. Okay, so actually, for doing this, we work with a scale problem. So it turns out that you can define this equivalent problem. You look at a new energy called E epsilon, omega epsilon. So if you minimize this energy subject to, so now we're looking at sets of constant area. It turns out you can relate this to the other problem. You have, so if you look at omega epsilon, you scale that to have the right mass. This will be a minimizer of the old energy. So that's fast, but this kind of makes sense that we can convert this into a problem of minimizing a new energy while fixing the area this time. Okay, and so why we do this is now, so this time we know the area is pi. And when n is small, epsilon is related to m like this. Or we have m equals epsilon to the. So basically when m is small, epsilon is small. So that's how these two parameters are related. So looking at the problem with m small is like looking at this problem with epsilon small. So you notice that if epsilon is small here, this term tends to drop out. So if you look at P of omega epsilon, so now this is the scaled minimizer that has area pi. So if you look at its energy, so again you can bound this, so it's less than 2 pi plus epsilon v0. So now this is just, we tested with a ball, so you can look at the ball radius 1 and plug this in here. So this is, again, something explicit. So now if you divide each side by 2 pi and subtract 1, it turns out you get the isoperimetric bound on the deficit of the minimizer. So I'm going pretty fast, but basically what this is if epsilon is small, right? So epsilon is like the mass, just rescaled. Then the deficit is also small, right? So now, I guess I won't go too much past this, but what we do is, so that gives us a bound on the deficit. And then if you know the deficit is small, Boneson's inequality will tell you that your minimizer lies in some kind of annulus like that, right? So it's like this, right? And so this delta V here is just the difference between the energy of the ball and the potential energy of the minimizer. So if you're in this small annulus, it turns out that you can actually bound delta V in terms of the isoperimetric deficit. So this is less than or equal to some function of the deficit. Right? So if the deficit is small, you're in this annulus, and if you can do some integral bounding to show that the potential energy of the minimizer and the ball can't differ by too much. And again, so we show that for epsilon very small, these inequalities should give you that actually the deficit is 0, and so is a disk. So that probably wasn't fully clear, but still, are there any questions on that? Okay, so the last thing I want to do is show you the actual paper. So I don't know if any of you know Professor Muratov at NJIT, but he's the guy who I work with. Okay, so one more thing I want to show you. So to summarize, right, we can look at parameter space, so you have alpha and m. So we have this one curve for non-existence. So for n large, there is no solution to the problem. And we also have this one curve for, so below this, below this we know that the solution is a disk. So when we look at this, we call this alpha 0. So where these intersect, right, it means that what? So here we have non-existence. And under this we have, if it exists, it's a ball. So then if alpha is smaller than this intersection value, well, if it exists, I think I drew these wrong. So let's see if it exists. Yeah, maybe these, I'll just show you the picture here, but. So first, remember when we were trying to bound the energy from above, we had all those convex functions. So I have a picture of that. So here we actually plotted them. So we took the minimum of this envelope. And so finally, this is like the big picture where we show everything that we know about the minimizers for different parameters.
Is it an electronic journal?
This is a Springer, like, annals of
I got published so
global-
fast. Did it create do a careful job?
Yeah. So we have this big picture now. So we did some extra stuff and we actually got some more information. So here's the curve. So yeah, I was drawing that wrong. So above this curve, we know that disk cannot be minimizers. So I think that was I called it MC1, right? So above this, you can't have a disk that's a minimizer. And let me so you can see. So by using the Euler-Lagrange equation, we could get a bound on convexity, and we found that there's this curve here. So for masses smaller than this, if there is a minimizer, it's convex. And then we have this here, so above this there, you can't have minimizers. And so if you look at this, right, so this is where above this, if there is a minimizer, below this, then if there is a minimizer, it's a disk. So if you look at this intersection, right, so for this is alpha. For alpha past this value, if there is a minimizer, it's below this curve, and it has to be a disk. And so we actually concluded that you can't have minimizers. So we did more than like I explained here, but basically what we did is we show that there's a certain critical value of alpha below which either there is no minimizer or it's a ball. Like I think it's not exactly clear in this picture, but how we did that, but we did. So the critical value of alpha is like 0.04 or something, and to find that you need to verify a bunch of inequalities, and that's where we use integral arithmetic. So we use Maple, and we use a bunch of upper and lower bounds. That's how we got that. So
some region is still open.
yeah, so we didn't do anything about like non-trivial minimizers. So we have no idea, like maybe somewhere here, there might be a minimizer, but it might not be a disk. So that's still an open question that you can look into like numerically or analytically. Yeah, I don't know. So, and lastly, I want to say that, so you can do this in more than 2 dimensions, and people have looked into that, but I don't think there's even less known about it than in 2 dimensions. And yeah, I guess I'm done. So thanks for listening.
Thank you very much. It's very impressive.